So in this session, now we are going to discuss another non-traditional optimization algorithm, that is artificial bee colony optimization algorithm. I think right day before yesterday we have discussed the ant colony optimization algorithm, where the behavior of the ants, right, those are mimicked in an optimization problem. So here we'll see in the ABC algorithm how the uh, honeybees behaviors they are captured and they are formulated as the mathematical equations to solve any optimization problem. So we'll see what are the basic phases in the ABC algorithm. So generally there are three phases in the ABC algorithm: employee B phase, onlooker B phase, scout B phase. So every phase we are trying to, find out a new solution from the existing solution. So there every phase they are having different operations, and how each phase will work, that we'll explore later. Then after the explanation of each and every phase of the ABC algorithm, we'll see one example how to solve the same sphere function whatever we have discussed for the differential evolution algorithm yesterday. We'll try to optimize the sphere function by using this ABC algorithm. So this ABC algorithm, this is also a right population-based meta-heuristic algorithm, uh, and that is introduced by Karabaga in the year 2005 for solving any numerical optimization problem. Generally, as I told, it was inspired by the intelligent foraging behavior of honeybees. How the honeybees they will try to collect honey from the food source, right? So that behavior we are trying to capture in this ABC algorithm. So generally, right, we are having some food sources in the ABC algorithm, or in the general foraging behavior of the honeybees. We are having some food sources. So honeybees they will try to explore the food sources, right? So same here, we are having three types of bees or three groups of bees. One is the employed bee, another one is the unemployed bee. So each employed bee is associated with a specific food source, right? And some onlooker bees will be there. So what they will do, they will watch the right dance pattern of the employed bees, and they will try to choose a particular food source depending upon the right dance pattern of the employed bees. Then the third type of bees, those are called your scout bees. They will try to source the food sources randomly. So onlooker bees, they are dependent on these employed bees, right, with a specific food source. They will watch the behavior of the employed bees, and they will try to collect nectar or the honeys from the food sources. Whereas the scout bees, they will try to source the food sources, or they will try to collect the honey, right, from the food sources randomly. So the employed bees, this is the first type of bees, the employed bees. They are associated with specific food sources, and there are two types of unemployed bee. One is the onlooker bee, and is the scout bee. So every bee, right, in the employee phase or onlooker bee phase or the scout bee phase, they will try to change the existing solution by using some mathematical
Madam, what
function.
is the function of onlooker bees?
I will tell, madam. Each and every phase we'll discuss one by one. Okay.
Okay, ma'am.
I will tell. The mathematical function I will tell it is there in the next slides.
No, ma'am, not the mathematical function, the social function.
Social function, what they will do, suppose some bees are there, right? Suppose five bees are there, B1 to B5, right? What they will, they are associated with a particular food source. Okay? Suppose they are trying to collect the some amount of honeys from the food source, right? So after collecting the food source, generally what happen, these employed bees, right? They will dance, right? Depending upon the pattern of the dance, this onlooker bees will try to locate from which food sources they have collected the honeys. That is the pattern. That means
Bulb. Ma'am, it is complex. Thank you.
this onlooker bee, they will follow the employed bees only, right? Whenever
Okay.
we'll see the mathematical function, you can understand, madam. That is the general behavior of the honey bees, right? They will collect the honey, and they do a particular dance. Depending upon the dance pattern, the unemployed bee or the remaining bees, they will try to locate the honey from those food sources. That is the general pattern or the foraging behavior of the honeybees. So when we solve the problem or when we'll explain the page, what is happening, you can understand that what is happening actually. So here the food source means a particular solution. If you are trying to locate, right, or if you are trying to match this foraging behavior of the honeybees with a mathematical or of the optimization problem, this food source represent a particular solution in the population. And every bee, they are trying to exploit the food source. It means every bee, they are trying to change the existing solution by using some mathematical function. That is the foraging behavior of the honeybees. So as I told, the onlooker and the scout bees, they are called the unemployed bees, right? So initially, what will happen, as I told, the scout bees, they are trying to source the food source randomly. So whenever we are having a population size equals to 5, right? So how you are generating the solutions? Those food sources we are generating randomly only, right? So randomly means the scout bees are involved by generating the random food sources. So this is if you relate to the optimization problem. So all the solutions, right, or the 5 solutions, if the population size equals to 5, they have to be discovered by the scout bees. I mean some by using some random functions. Right? So what will happen? The nectar of the food sources are exploited by the employed bees and the onlooker bees, and this continuous exploitation, this will ultimately cause them to become exhausted. So what is the meaning here? Some food source is there, right? So from this food source, some employee bee is there. So this employee bees, they are collecting honey, or this is a nectar means that is the honey they are collecting from this food source. So by seeing the dancing pattern of the employed bees, some onlooker bees will be there. Again they will try to collect the nectar or the honey from the same food sources. So what will happen due to this continuous exploitation? What will happen? These food source, the amount of nectar whatever is present in the food source, it becomes exhausted. So what will happen next? We have to search for the new food source randomly. So that is the meaning of this case, right? So then the employed bees, which was exploiting the exhausted food source, it becomes a scout bee in search of further food sources once again. I mean, if the nectar amount, right, is exhausted in the food source by continuously exploitation by the employee bee and the onlooker bee. So whatever employee bee we are having, they will become a scout bee, because scout bee, they will search the food sources randomly. Right? So in the ABC, in the artificial bee colony optimization algorithm, right? So the position of the food source, it represents a possible solution of the problem, right? As I told, and the nectar amount of food source, it represents the quality of that solution. So quality of that solution means how you are determining the quality of the solution. That is the fitness value of that solution, right? We are having the objective function. From that objective function, we are calculating the fitness value of the associated solution. Right? So the number of employee bees is equal to the number of food sources. So whatever number of solutions are there in the previous, right, in the differential evaluation algorithm or the genetic algorithm, if our population size, right, population size or the swarm size, if the ant colony optimization, this is 10. So 10 solutions we are generating, randomly 10 solutions we are generating. But in the ABC algorithm, if the swarm size, right, swarm size equals to 10, so we have to consider number of employee bees equals to 5 and the number of onlooker bees equals to 5. Right? And the scout bee phase, we'll see later whether the scout bee phase is optional. It depends upon the employee bee phase and the onlooker bee phase. So the scout bee phase functionality is different. We'll discuss later how the scout bee phase is happening. Right? So if the swarm size equals to 10, we have to consider the employee b equals to number of employee b equals to 5, number of onlooker b equals to 5. And one thing in the every whatever algorithms we have studied so far, we are considering about the quality of the solution. We are right. We are measuring the quality of the solution by using the objective function or the objective value. But here we are dealing with the fitness value. So some function is there. So here objective value and the fitness value are different. So first we have to define the objective value using the objective function. From the objective value, we have to determine the fitness value associated with individual solution. So this fitness value, of individual solutions are used for greedy selection or for determining any other decision or doing any decision during the latter phase of the ABC algorithm. So if you see this algorithm, now you will get some idea how what is happening in the ABC algorithm. So we are having some fitness function. That function, right? We are trying to minimize or maximize. We are having n number of decision variables or the design variables. So for every decision variable, we are having the lower bound and the upper bound, right? NP, this is the population size. Capital T, this is the number of iterations that we can consider as the termination criteria. So here one another parameter is there, that limit. So depending upon the limit value, we have to decide whether the third phase, that scout B phase, whether we have to perform or not. So that we'll discuss later. Okay? So let us see the overview or the abstract of this algorithm. Then what is happening each and every phase we'll explore. So what we have to do, you have to initialize a random population first, right? Then we have to evaluate the objective function and the fitness value of each solution in the population. Suppose we are having five solutions are there in the population. So for every solution, we have to first determine using the objective value, using the objective function. Then there is some formula to calculate the fitness value. So this fitness value will calculate. So that will be used in the latter stages of the ABC. Then another parameter we are using in the ABC, this is the trial counter, right? So this trial counter is initially set to 0 for all food sources. So all food sources means all the solutions, right? So for what purpose we are using this trial counter, right? As we are saying, every B, it may be the employee B or it may be the onlooker B, they will try to exploit the food source. That means they will try to change the existing solution, right? So during the modification of an existing solution to a new solution, if you are getting a better solution, then this trial counter will be reset to 0. Otherwise, that means we have done some, we have applied some operation and we are unable to get a better solution, right? So in that case, we are failing, right? We are unable to get a better solution. So there is a failure. Whatever modification you are doing, it has no use. So we are failing to get a better solution. So in that scenario, you have to increment the trial counter, right? So this trial counter is used to determine whether the new solution, whatever we are generating, is a better solution or this is an inferior solution. If it is a better solution, we are resetting to 0. If this is an inferior solution, we are incrementing the trial counter by 1. That means this trial counter associated with every solution determines how many number of failures happened if we are trying to modify that solution, right? So depending upon the relation between this limit and the trial, we have to decide whether you have to go for the scout B phase or we have to stop there, right? So there are, if more failures are there, right? If more failures are there compared to the limit, then we have to go to the scout B phase. Otherwise, we have to stop there. No need to go to the scout B phase. So let us try to understand what is happening in the inside in the ABC algorithm. So as I told, we are having three phases. So for every iteration, for small t I equals to 1 to capital T, for every iteration, first we have to do the employee B phase, right? So perform employee B phase of all food sources means, suppose we are having five solutions we have generated initially, S1, S2, S3, S4, S5, right? So we'll employee B phase we are applying means we are trying to modify the existing solution. So S1 dash, S2 dash, S3 dash, S4 dash, and S5 dash. So whichever is better, right? Then we are doing the greedy selection between S1 and S1 dash, S2 and S2 dash, similarly S5 and S1 dash, and the better solutions are the output of this employee B phase. Suppose between S1 and S1 dash, assume S1 dash is better, S2 and S2 dash, assume S2 is better, 3 and 3 dash, maybe S3 is better, assume S4 dash is better, and S5 dash is better. So this is the new population we are getting after performing the employee details, right? So how to do the modification from S1 to S dash, similarly S2 to S dash, up to S5 to S5 dash. So we'll see the detailed working principle of the employee B phase in the next slide. Right. So this we are doing in the employee B phase. We are having 5 solutions. Initially we have generated randomly. We are doing some mathematical operation on these 5 solutions to get another set of 5 solutions. Then we are doing the greedy selection between the old solution and the newly generated solution. Whichever is better, we are keeping as the output of the employee B phase. Right. So we have started with 5 solutions. After performing the employee B phase, again we are getting 5 solutions. Right. Next, what we have to do? Next, we have to perform the onlooker B phase. So, in order to do the onlooker B phase, we have to determine the probability of each food source. So, here food source means your solution, right? If you remember in the genetic algorithm, you have done the selection, the roulette field selection, right? It is similar to that one. That means the probability of the solutions which is high. There is a chance that we are trying to explore or exploit those food sources or those solutions more than once. That is the meaning of the probability. So there is some mathematical equation to find out the probability of each solution in the population. So we have to determine the probability before performing the onlooker B phase. Right. Now this S1 dash, S2, S3, S4 dash and S5 dash, this is the input to the onlooker B phase. Now we have to perform the onlooker B phase. Right. Onlooker B phase. So in the onlooker B phase, again we'll do some mathematical operation to convert, right? That means we are trying to change the solution. Suppose this is S1 double dash, S2 double dash, S3 double dash, S4 double dash, S5 double dash. So some mathematical operation will perform here to change these solutions into a new solution. Again, we have to apply the greedy selection between S1 dash and S1 double dash. So whichever is better, right? That will that will provide us the output of the onlooker B phase. Suppose S1 double dash is better, S2 is better between S2 and S2 dash. Between S3 and S3 double dash, assume S3 double dash is better, and suppose this is S4 is better, S5 double dash is better. Assume this is the assumption only, right? Okay. So this will happen, right? So what we are doing now, we have started with the 5 solutions. We have applied the employee B phase. Again, we are getting another population where 5 solutions are there. Again, we are performing the second phase of the ABC algorithm, that is the onlooker B phase. Again, what we are getting? Again, we are getting another population of 5 solutions, right? So always we are trying to add the better solutions into this population, right? In between that, we have to update the trial counter, right? Suppose this during S1 dash and S1 double dash, we are getting that S1 double dash is better. That means whatever modification we have done, right? There is no failure. No, we got a success. That means we are able to achieve better solution if we are applying the onlooker B phase. So the trial counter associated with the solution will be reset to 0. So that is the purpose of the trial counter. And in this scenario, if you see S2, between S2 and S2 double dash, if you are comparing, right, you have applied some mathematical function to convert S2 into S2 double dash. But after doing that mathematical function, you are getting that the previous solution is better, right? That means we are getting a failure. We are trying to explore the solution, but we are unable to get a better solution. So the trial counter of this solution, second solution, will be incremented to 1. That is the meaning, right? So after doing the onlooker B phase, assume this is the output of the onlooker B phase. So you have to memorize the best food source. So whichever is best out of this 5, you have to memorize that information. Otherwise, the best result, whatever you are getting in every iteration, that may lose during the subsequent iterations. Right? Then after doing the onlooker B phase, we have to decide whether you have to go for the scout B phase or you have to stop here. So how to determine? So that condition is we are having 2 parameters here, limit and trial, right? If trial of any food source is greater than the limit, that means more number of failures we are getting, right? We are trying to modify the solution, but we are getting more number of failures. So for that solution, if it is happening, then we have to perform the scout B phase of the exhausted food source, right? So the trial value, whichever is greater than the limit for any solution, that solution can be considered as a scout B phase. So what we have to do, we have to again do some operation in the scout B phase. Suppose this is the output of the onlooker B phase. So here we will determine whether we have to go for the scout B phase or not. If we are doing the scout B phase, so something we have to done on this population, some mathematical operation we have to do on this population, and we'll get again a new population. Assume that is the, suppose we are getting C1, C2, C3, C4, C5. So this is the output of this ABC algorithm. We have started with 5 solutions. We have done employee B phase, we have done onlooker B phase, we have done the scout B phase, and at the end again we are getting a population of 5 solutions, right? So always we are memorizing the best food source, right? So whatever the best food source, every iteration we are memorizing. So at the end, after the termination criteria is satisfied, we have to output the optimum solution as the best food source we achieved so far. So this is the basic outline of the ABC algorithm. Now the question is that how to perform, or what is happening in the employee V phase, what is happening in the onlooker V phase, what is happening in the scout V phase, right? How to calculate the probability, those things detailedly we'll discuss. So phase by phase we'll discuss. So generally this is the flow chart, whatever the overview of the algorithm we have discussed, right? So we have to initialize the parameters. So initialize the parameters means we are having population size, termination criteria, right? Then we see whether the termination criteria is satisfied. If the termination criteria is not satisfied, then whatever the best solution we achieved so far, right, that will be the optimum solution for the given problem. If the termination criteria is not satisfied, we have to perform the 3 phases of the ABC algorithm. The first phase is your employee B phase, so update the employee base. That means we are performing the employee B phase. Second is the, we have to update the onlooker base. That means we have to perform the onlooker B phase. Third one is we have to update the scout phase or the scout B phase, right? Then we are memorizing the best solution, and again we are coming back to this to check whether the termination criteria is satisfied or not. So this is the basic flow chart of ABC algorithm. Now let us see what is happening in every page of this ABC algorithm. So first we will see in the employee B phase what is happening, right? So now assume we are having 5 solutions. Initially we have generated 5 solutions, S1, S2, S3, S4, S5. So these are my 5 solutions, right? So in the employee B phase, what is happening, right? So the number of employee Bs is equal to the number of food sources or number of solutions. So we are having 5 employee Bs, EB1, EB2, EB3, EB4, and EB5, right? So in the employee B phase, every employee B is associated with a particular food source. That is the meaning, right? So there are 5 employee Bs and there are 5 food sources. So every employee B is associated with a particular food source. So what they will do, they will try to exploit the amount of nectar present in the food sources. So what it means mathematically, this EB1 is trying to modify the solution S1. EB2 also trying to modify the solution S2. Similarly, EB5 is trying to modify the solution S5. So for doing that modification to the existing solution, we want some mathematical function, right? As in the previous algorithms we have seen, we are trying to change all the decision variables value, right? Suppose we are having the sphere function, yesterday we have discussed, right? We consider dimension equals to 4, x1, x2, x3, x4, right? Suppose 2, 3, 4, 5, these values are there, right? So what we have to do, in the employee B phase of the ABC algorithm, only a single variable we are trying to change. That means the EB1 is trying to change one single variable or the decision variable in the solution. It is not changing all the variables, right? It is changing a single variable. So let us see what is happening and how it is changing. So as I told, the number of employee B is equals to the number of food sources. So here 5 food sources or 5 solutions are there. We are having 5 employee Bs, right? So all solutions get an opportunity to generate a new solution in this phase. That's why every employee B is associated with individual solution. So we are giving equal opportunity to all the solutions to undergo some changes, right? So how does changes we have to do? For that, a partner is randomly selected to generate a new solution. Suppose we want to change, we miss the EV1, employee B1 want to change the first solution. Assume the first solution is 2, 3, 4, 5. So what it will do? It will generate a partner randomly from the population. So that the pattern or the partner must be different from this S1, right? We are having the population size 5. So you want to change the S1 because S1 has to undergo the employee B phase. So the partner must be considered from the 2, 3, 4, 5. That should not be equals to the food source which we want to apply the employee B phase, right? So the partner and the current solution should not be same. So we can consider the partner equals to 3 also, right? Then how to do the modification in the S1? So the new solution is generated by modifying a randomly selected variable. So we are not modifying all the decision variables present in the solution. Only a single variable we are trying to modify. So which variable you have to modify, that also you have to decide, right? So assume here jth jth decision variable you want to change, right? So xj new, that means 2, 3, 4, 5. Assume our j equals to 1. So this bit we want to change from the existing solution 2, 3, 4, 5. So what will be the new bit now? This xj new, this equals to the old value xj plus 5 into xj minus xjp. So xj is the jth bit of the current solution and xjp is the jth bit of the partner. Suppose now we are having 5 solutions. So this is my solution 1. Solution 2 is suppose 1, 2, 3, 4. Solution 3 is, I am writing randomly only, 3, 4, 5, 6. S4 is 1, 6, 3, 2. S5 is 6, 7, 2, 3, 5. Assume this is my population. I have generated this population randomly. Okay, I want to apply the employee B phase to the solution 1. For which variable? For the variable 1. Assume I have select the partner as this one. This is my partner. Okay, so what now this bit I want to modify. So this bit, this new bit, xj new, right? That means your x1 new. For the solution S1, what is the x1 bit now? This equals to xj. So the previous value or the current value is 2 plus 5 into what is the current value? 2 minus the partner is the third solution, and for the partner the first bit is 3. So 5 into 2 minus 3, right? So this mathematical equation you have to solve to find out the new value of this first decision variable for S1, right? So where xj new, this is the jth variable of the new solution. Xj is the jth value of current solution. Current solution means which has to undergo the employee B phase. Xpj, this is the jth variable of partner. So phi, this is a constant, like this equation looks like yours, what you call mutation operation in the differential evaluation, right? But here we are changing differential evaluation, all the decision variables we are changing, but here only a single bit we are changing. So the phi is the constant, that is the range in between -1 to 1, right? So after doing this one, after applying this operation, right, if we are taken the input, right, we are having the lower bound, we are having the upper bound. After doing this mathematical function, if the value it is exceeding UV and this is beyond the LB, right? So here you have to do the kernel bounding. That means your xj new equals to LB. If the xj new is less than LB, the xj new equals to UB if xj new greater than UB. Right? So this is the simple mathematical equation you have to follow in the employee B phase. Same thing also you have to do in the onlooker B phase, where the pattern is different. And when to do that phase, that is different. Right? So one random bit on one random decision variable you select which you want to change for a particular solution. Then you choose a partner. So the partner must be different from the current solution. Then you use this mathematical function. The new bit, new decision variable equals to old value of the decision variable for plus phi is a constant into the difference between the current solution and the partner solution with respect to the jth bit, right? So this is the employee B phase working principle. So after doing this thing, after doing the corner bounding, right? So suppose 2 3 4 5. Now after doing this operation, suppose we are getting 3 3 4 5, right? Now what you have to do, as I told you, so this is S1, suppose this is S1 dash. We have to do the greedy selection between S1 and S2. So whichever is better, that we have to keep in the population, right? And if 3345 is not better than 2345, so we have to update the trial counter of this solution by 1. I mean, we have to increment the trial counter of this solution by 1, because we have tried to change the solution, but we are unable to get a better solution, so we got a failure. So the trial counter will be incremented by 1. If this is a better solution, the trial counter will be reset to 0. So this we have to do in the employee B phase. So right, so this is the pseudocode of the employee B phase. Same your fitness function, lower bound, upper bound, population size, objective value, fitness value, trial. So trial will determine the number of failures you have encountered when you are trying to change a solution. Right? So what you have done? So for every solution in the population, for I equals to 1 to NP, you are randomly selecting a partner such that partner must be different from the current solution, such that I not equals to P. Then what you have done? You have randomly select a variable j, right? And you are trying to modify the jth variable. So how you are doing that jth variable? That equation xj new equals to xj old value plus phi into xj minus xjp partner, right? So that you have to do. Then you bound the newly, whatever the decision variable value you are getting, you have to bound that one, right? Corner bounding you have to do. Then you have to come to the grid selection. So whenever we are doing the grid selection, we are not comparing with the objective value, remember, we are comparing with the fitness value, right? So if you are, the new solution is better, then the trial counter we are resetting to 0. Of the new solution is not better, we are getting a failure, so the trial counter will be incremented by 1. So this is the basic things you have to do in the employee B phase. So after this, you have started from a population of size assume 5. Again, you are getting another population of size 5. Maybe some of the some of the old solutions are coming to the new population, or some of the solutions after doing the employee B phase you are taking to the population. Okay. Next, after doing the employee B phase, you have to go for the onlooker B phase. So the before doing the onlooker B phase, you have to determine the probability value of individual food source, or the probability value of individual solution. So how to do that one? So the probability value of each solution to undergo the onlooker phase is this one. The probability of ith solution will be 0.9 into feet of phi divided by maximum feet plus 0.1. Okay. So the probability values of all the solutions are determined before the onlooker phase. So this is similar to your roulette wheel selection. A solution with higher fitness value will have generally the higher probability. So higher probability means that the fitter solutions, or the probability value is high, they may undergo the onlooker phase more than once. So these things we will see whenever we will solve the example. You can understand how the solution having the higher probability is undergoing the onlooker phase more than once. We will see in that example. I will explain you how it is happening. Because theoretically, if I will tell, you can't understand. So in the example, whenever we will solve, we'll find out this one. How one of the solution having the higher probability is undergoing the onlooker B phase more than once. That means the better solutions we are selecting to the next population. That is the meaning. So what you have to do in the onlooker B phase, now we are having 5, right? Assume S1 dash, S2 dash, S3 dash, S4 dash, S5 dash. Assume these are the output of our employee B phase. So we are having now 5 onlooker B, OB1, OB2, OB3, OB4, OB5. Right? So every solution has to go the onlooker B phase, onlooker B phase in this phase. So what we have to do for that? This OB, onlooker B, it will try to exploit the food source. That means it will try to change the solution S1 dash. So when it will change the solution, So we are having the probability value associated with each solution. We have determined, right? By using this one, we have determined the probability value. So if OB1 is trying to explore the solution S1 dash, it will generate a random number R which follows the uniform distribution in the range 0 to 1. If this R is less than the probability of 1, because it is trying to explore the first food source, right? If R is less than P1, probability of food source, then OB1 can change the solution S1 dash. So how it will change? Same like whatever we have done in the employee B phase, we have to define which design variable or the decision variable we want to change. Then by using the same function, that partner we have to select. Then by using that old value xj plus phi into a difference between the old value minus the partner value. That equation we have to follow. Assume R is not less than P1. Suppose this is happening OB1 for the onlooker B1, R is less than P1. So for this solution, our onlooker B phase is over. Now for the second solution, we have to do the onlooker B phase. Now for this, OB2 is associated with S2 dash, right? Now, so it will generate again a random number and it will compare with your P2, probability of second solution. If R is less than P2, then it will explore by using the same function whatever we have defined in the employee B phase. But if R is greater than P2, what will happen? It cannot exploit the forces S2 dash. That means OB2 will not get a chance to change the solution S2 dash. So what it will do? It will try to explore the next solution S3 dash. Right? So this is the difference in the onlooker B phase. So now again it will generate a random number R. Suppose R is less than P3. Right? If R is less than P3, then it will try to explore. Explore means it will try to change. Right? Next come to your OB3. Now up to S3 dash we have changed, right? Now OB4, it will try to exploit this one, S4 dash. Again, if this, it will generate a random number. If this random number is greater than P4, so what will happen? OB3 will not get a chance to change S4 dash. So what it will do? It will go to the next one, S5 dash. So it will try to explore the next food source in the population. Again, it will generate a random number R. If this is less than P5, so it will explore S5. Right? So up to S4, this is over. Right? Sorry. Up to S5, this is over. But the next is there is a OB4, right? So the onlooker B4, what it will do? Now till now, your solution 5, OB3, change the solution S5. So again, it will come back to the first one. So OB4 will get a chance to explore the solution S1 dash, right? Now what it will do? It will generate a random number. If this random number is less than P1, again it will get a chance to this one. So if you remember this statement, right? Higher probability solution may undergo onlooker phase more than once. If you see here, sorry, if you see here, this S1 dash, right? This solution, right? Maybe the probability value is higher. That's why, right? This R, right? Probability value is higher. That's why this S1 dash, we are doing two times changing to the S1 dash because this probability is higher, right? Next, after doing this OB4 by changing the S1 dash, then OB5 is remaining. So OB5 will try to explore the solution S2 dash. Again, if this will generate a random number, if this is less than the probability of P2, it will unable to explore S2 dash. So what it will do? It will explore, try to explore S3 dash. Now, if this R is less than P3, it will explore. Otherwise, again, it will try to explore the next food source. So this will happen till every onlooker B will get a chance to change one of the solution in the population. So whenever we are doing, right, we are changing the solution in the population by using this onlooker B phase. As we have done in the employee B phase, we have done a greedy selection, right, with the previous one with the modified one. Whichever is better, that we have to keep in the solution. And if you are getting a failure, that means we are unable to get a better solution. So the trial counter we have to increment by 1. Otherwise, the trial counter we have to reset to 0. Because depending upon this trial value and a user defined parameter limit, we have to decide whether we have to go for the next phase, that is the scout B phase or not. Right? So this is the basic principle of the onlooker B phase. So whatever we have discussed, that is there in the pseudocode. So the same your fitness function LB, UB, NP, P is the right then the F is the fitness value, fit is the objective value, fitness value, this is the probability value, trial, right? This is the counter, that counter you have to use to decide whether uh, uh, you have to go for the scout B phase or not. So NP is the number of population, right? This is not required. Okay. P is the partner. Sorry, P is used for representing the partner, because we have to choose a partner for doing this modification. NP is the population size, the number of population. P is the partner. So what you have to do, you set the M equals to 0, N equals to 1, right? So while M less than equals to NP, so first this one you remember, OB1 is trying to exploit this S1 dash, right? So you generate a random number R. If this R is less than the probability of N, because N equals to 1, right? We are starting from the first solution. If this R is less than the probability N, so we have to change. OB1 will get a chance to change the solution S1 dash. So for changing the solution, if you remember, this thing we are doing in the employee B phase. So this is the part whatever we have used in the employee B phase. What we have to do? We have to select a random partner such that n not equals to p. So whatever the current solution you want to modify, that should be different from the partner. Second, we have to randomly select a variable j, and we want to modify the jth variable. So for that we have to use that equation xj new equals to xj plus phi into xj minus xjp. This equation we have to use. After that we have to bound, right? Then we are comparing whether we have to consider the old one or we have to consider the new one. That means we are doing the greedy selection between xj and xj new. Okay, so depending on the fitness value we are getting. If we are getting a better solution, so the trial counter associated with that solution we are resetting to 0. Otherwise we are resetting or incrementing the trial counter by 1. Next step, if you are right, this is getting a chance, this OB1 is getting a chance to exploit S1, then what we are doing, we are going to the second onlooker B. So that's why this M equals to M plus 1. That is for next onlooker B. After that what we are doing, we are going for, after the n equals to n plus 1, because we are moving to the next solution also. So M for your onlooker B, n for solution, right? So reset n equals to n if the value of n is greater than np, because we have seen this OB3 after exploiting this S5, right? What we were doing, this OB4 it is getting a chance to exploit this S1 dash. So for that purpose, reset n equals to 1, the value of n is greater than np. So this is the n. So with this, if you apply this one, right, with this S1 dash to S5 dash as the input for the onlooker B phase, again you will get, right, S1 double dash, S2 double dash, S3 double dash, S4 double dash, S5 double dash. So whichever is better between the right in input of the onlooker B phase and this is the changed value of the onlooker B phase, whichever is better, those are kept in the population, right? So with this, your onlooker B phase is over. Now every solutions we are maintaining the trial counter, right? So the trial counter is reset to 0 whenever we are getting better solution, and the trial counter is incremented by 1 whenever we are getting a failure, I mean we are not getting a better solution. So depending upon the trial counter and the limit value, we have to decide whether we have to go to the last phase, that is the scout B phase, right? So for that we need a parameter, that is the limit, user specified parameter. So generally the limit value is, whenever you will do the experiment, you will keep this as NP into D, that is the number of population into dimension of the decision variables, right? So if the trial counter, right, if the value of trial counter is greater than limit, then that solution can potentially enter into the scout B phase. So what is the meaning? So out of these 5 solutions after the scout B phase, sorry, onlooker B phase, suppose S1 double dash, this is the trial counter. Okay. S2 double dash, S3 double dash, S4 double dash, S5 double dash. Suppose the trial counter is 0, 1, 1, 2, 1. Okay, and suppose the limit value, we are considering a small value, assume 2. Generally, whenever you will do the simulation, you keep this higher value. For this hand calculation, I am keeping a small value so that you can know what is happening in the scout prefix. So the limit value is 2. Okay, and assume suppose this is 3. Limit value is 2, and this is S4 dash, the trial counter is 3. So the trial counter of any solution is greater than limit. So this is actually greater than equals to, not greater than equals to limit. So this solution can potentially enter into the scout phase. That means this solution we have to discard from the population. So this we have to do in the scout B phase. So in the scout B phase, any solution trial counter is greater than equals to the limit value, that solution or that food source is exhausted. So we have to discard this solution with a new solution. We have to replace this solution with a new solution, right? So the trial counts of the abandoned solution is reset to 0. So abandoned solution means this one. We are replacing this S4 dash with a new solution, new S4 dash, right? We are replacing this one with a new solution, and this trial counter, it was previously 3. Now we are changing the trial counter to 0, reset, right? So on the scout phase, your solutions with trial value greater than limit are the candidates to be discarded. One solution with trial greater than the limit is replaced with new random solution, so greater than equals to this. So trial counter of newly included solution is reset to 0. So how to replace, right, this one? How to replace this solution with a new one? So that is, as I told, the scout B phase, it will search the food source randomly, right? So thus replacement also we are doing randomly. So random solution, how you are generating? So this is the random solution, or the generating the random solutions, we are using this equation. Xk equals to lower bound of the decision variable plus ub minus lb into random. Generally, whenever you generate the population, initial population, if you use this limit lower bound and the upper bound, and you will use this lb plus r into ub minus lb, so your uh, random initial random population will be generated. So in the scout v phase, right, we are providing the fitness function as the input, lb ub, trial value of each solution, limit user specified value, right, and p is the population from the population, right? So you have to identify the food source k which trial is greater than limit, greater than equals to limit. Then you have to replace the sk from the population as with this one, and you have to reset the trial value of this xk equals to 0, and whatever fitness value you are getting, you have to keep this as 0, right? And the best solution you are memorizing after the onlooker b phase, right? So before doing the scout b phase, you have to memorize the best solution, otherwise the optimum solution value you may lose whenever you are doing the iterations. So after doing this scout b phase again, right, suppose you are getting another population of size SC2, SC3, SC4, SC5. Now you have started from S1, S2, S3, S4, S5. You have performed the employee B phase. Again, you got another solution. You have performed the onlooker B phase. Again, you got another population. If there is a chance to do the scout B phase, after doing the scout B phase, again you are getting another population. And every iteration, you are memorizing the best solution, right? So for the next iteration, now this is the input population. So the same steps you have to repeat until your termination criteria is you are able to reach the termination criteria. And every iteration you are updating the best solution. So at the end, the optimum solution is the best solution achieved so far throughout the iterations of the ABC algorithm. So this is the theoretical concepts of the ABC algorithm, how to perform the employee B phase, onlooker B phase, scout B phase. Let us do solve a numerical example so that you can get clear idea what you have to do. The same sphere function I am using. So my target is to minimize the sphere function, this one, right? Minimize f of x, where f of x is summation of I equals to 1 xi square. So the same dimension I am considering as 4, 4-dimensional problem. Lower bound is 0, upper bound is 10. So how to calculate the fitness value? This is the just you have to take the squares of individual decision variables and you have to take, right? So our decision variables are x1, x2, x3, x4. So apart from that, what you want? You want the parameters. You have to initialize the parameter. So let the swarm size equals to 10. So if the swarm size equals to 10, you are having the employee B, number of employee B equals to 5, that is the S by 2. Okay. And the number of onlooker B also 5, that is the S by 2. This you have to take care. So that means my population size, this is the swarm size. Swarm size means how many number of bees are there, right? And the population size is how many food sources are there or how many solutions are there. So the employee B equals to 5 and the OB equals to 5, then we are having the population size equals to 5. So S1, S2, S3, S4, S5, and we are having 4 dimensions x1, x2, x3, x4, right? So let us assume the termination criteria capital T equals to 10 after 10 iterations, right? We have to stop the algorithm. Assume the limit value, I am considering a small value so that I can show you the calculation, hand calculation. And NP is the number of food sources, I mean the population size. And generally, this already I told you, whenever you will solve any problem, right? So that time you consider the limit value equals to population size into dimension. So for this problem, what will happen if you want to simulate it, right? NP is the population size 5 and D is the number of dimensions, right? 20. Limit value you have to get 20. And you have to do for a large number of iterations, not for 10 or 20, right? You have to do for 1,000, 10,000 iterations. Then only you can see the effect of this limit and the trial, and you can determine whether you have to go for the scout B phase or you have to stop after the onlooker. Okay.
Ma'am, can you please explain it once again? Limit NP into D.
This limit value, whenever we'll consider, generally if your problem you are considering the population size equals to suppose 5, okay, my population size equals to 5, and number of decision variable or number of design variables equals to also 4 for this particular problem. We are considering 4-dimensional problem, right? X1, x2, x3, x4. So the limit, generally you have to initialize with this NP into D. Higher value you have to initialize. Here I have initialized just to show the hand calculation, nothing else, right? Whenever you will solve any real life problem, you have to take the limit value to a higher value. This one is very less, right? That means even if you are trying once to modify a solution and you are unable to get a better solution, that trial will be one, right? So that solution also you are discarding. So that is not our purpose. So our purpose is if more number of changes we are doing and more number of failures we are getting, in that scenario you have to discard the solution. So that is the meaning here.
Okay, ma'am. Okay.
And limits would be your population size into your dimension of the decision variable, right? Here I am choosing one to show only for understanding what is happening, that I am keeping for hand, because we are doing the hand calculation we are doing. Yes.
Okay, ma'am.
Okay. So with this parameter initialization, now let us see how to solve this problem, how to proceed. So as I told, our swarm size equals to 10, right? So our population will be 5. Employee, number of employee B is equal to 5 and number of onlooker B equals to 5. So the total swarm will be 10. That is the meaning. Okay. Okay. Now our lower bound is 0, upper bound is 10. Okay. And what we have to do, as you remember the pseudocode of the ABC algorithm, first you have to initialize the parameters, right? We are having our objective function is there, LB value is there, UB value is there, termination criteria is there, limit value is there, right? So what we have to do, we have to generate the initial population having size 5 because we have considered NP equals to 5 here. Now how many solutions are there? You see, first, second, third, fourth, fifth, S1 to S5. How, what is the dimension? 4 dimensions are there, x1, x2, x3, x4. Now if you see all the values of x1, x4, x1 to x4 in every solution, it is coming in the range 0 to 10. So that one we can generate by using this one only. I think Prakash sir already told how to generate that one in the MATLAB optimization toolbox. If you use this one, you can generate randomly these values. All the values it will come in the range 0 to 10. Okay. So this we are generating randomly. Next, what we are doing, we are determining the objective value associated with each solution. So this is simply that x1 square, x2 square, x3 square, x4 square. So this will be 16 plus 0 plus 1 plus 64. So 17 plus 64, 81. Similarly, you can calculate the objective function value. Next, what we have to do after doing this, as I told, we have to calculate the fitness value of the population, individual solution in the population. So the fitness equals to 1 by 1 plus f if f greater than equals to 0, 1 plus absolute of f if f is less than 0. So by using this, you can do the greedy selection between the two individual solutions in the employee B phase as well as the what you call the onlooker P phase. So by using that formula, now you calculate the fitness value of the population. So you remember we are using the fitness of the population for doing the greedy selection. Okay. Okay, this is only avoiding zero. If some fitness value is zero, na, in order to avoid that zero fitness value only, we are calculating the fitness of the population by using this mathematical function. If something is less than zero also, right? In order to avoid that one, we are calculating the fitness of the individual solution. Next, what you have to do, if you are remembered, there is a trial counter associated with individual solution, right? So initially, the trial value of each solution is 0. Now let us add that one. Now this is the trial, right? So generate the initial trial vector of the population. So it generally for what purpose we are using the trial vector? It will correspond to the number of failures encountered by that particular food source, right? So the trial counter of individual solution is initially all at 0. Okay, just 1 minute. Okay. So the trial counter of individual solutions are 0 now. Right. Next, what you have to do? Next, we have to go for the employee B phase. So we have to perform the employee B phase. So employee B phase means what? If you remember, so in the employee B phase, every employee B is associated with a particular solution. That means we are trying to modify every solution in the population. So let us try to modify one by one solution in the population. So the first solution is 4018. So for this 4018, we want to find out the modified solution. So how to do that modification? For that, if you remember, we have to decide which bit we want to change or which decision variable we want to change. We have to choose a partner, right? Then we have to determine xj new equals to xj plus phi into difference between xj and xj partner. These are the things. Then we have to do the bounding. Then we have to do the greedy selection between the old value and the new value. So let us do the calculation for 4018 and we will see how this 4018 after performing the employee B phase, what is the change in this first solution, right? Now we are performing the employee B phase for 4018, right? So let us assume the third variable we want to change. Let us say. So select a random variable to change, that the let the variable is 3. So there are 4 variables. We want to change the third variable, right? So the third variable value in the current solution is 1. That means your xj equals to 1, right? So this variable we want to change. So what is the value of xj new? This we want to find out, right? So in order to find out that one, what we have to do? We have to select a partner and that partner should not be same as that solution. So the first solution we want to change. So the partner, it must be some other solution in the population. So the partner is the fourth population or the fourth solution. If you come back to that table, so fourth solution is this one, you see, 2149. We want to change this third bit, right? So we have to do that mathematical operation between this and this, and we'll get a modified value. And we want that 5 value also, right? Now we see. So 2149, this is the fourth part, this is the partner. So xj new equal to xj plus 5 into difference between the current solution and the partner solution, right? So if you perform that one, as I told, the phi value, it should be in the range -1 to 1. This is the user defined value. So you can take any value in the range -1 to 1. So what will be the new solution? So here we have considered the phi equals to 0.81. So the first solution, third bit, right? Because we are trying to change the third decision variable. This will be old value plus phi into old value minus partner's third bit variable. This is the 2149. First one is 4018. 4018. Partner is, I think, 2149, right? 2149. So this bit I want to change, right? So 1 plus phi is 0.81, 1 minus 4. This is the third bit of the decision variable. So you will get some value. So here we are getting minus 1.43. So if you see minus 1.43, after that you have to do the bounding, right? Minus 1.43, this is coming below 0, right? 0 to 10 is our given lower bound and the upper bound. So this value you have to bound. Bound means forcefully you have to bring this value as the 0, right? So the value is 4008. So our original solution is 4018. So this solution undergoes the employee B phase and we got 4008. So this is the modified solution. Now we have to see whether this is a better solution or this is a better solution. So we have to compare between this solution. Whichever is better, that will go to the next population, right? So that is the basic concepts in the employee B phase. Right? Now what you have to do, you have to evaluate the fitness value of the new, you have to evaluate the fitness value of the old. So as you're seeing the new value, this is better than the x1, the previous value. So the trial of one, solution one is reset to 0. Right? Now you see, this is the output. So if you remember, its previous value was 1, right? So after performing the employee B phase, this value is 0. And this trial counter set to 0 because it was initially 0. So we have set it to again 0. So this is the employee output of the employee B phase after applying to the solution 1. That means EB1, right? Employee B1 tried to modify the first solution 4018 and it is able to get a better solution, that is 4008. So what you have to do? So with this, it completed the employee B phase for the first solution. So same steps you have to follow for the second solution, third solution, fourth solution, fifth solution, right? So for every solution that has to undergo the employee B phase, you have to do some steps, right? What steps you are doing? Which variable you want to change? You have to select a partner, right? You have to find out the modified bit, then you have to do the bounding, then you have to do the greedy selection. Then depending upon the greedy selection, this trial counter you have to either reset or you have to implement, right? So for the remaining solutions, I am not going to show you the calculation, only I will tell you if this is a better solution, what will happen. If this is not a better solution, what will happen. Okay? Let us do that one. So 3197. Now we have to perform the employee B phase for the second solution, that is 3197. So whatever I told, right, how in order to undergo the employee B phase, you select a random variable, let the variable is 1. These are all randomness, right? This is in your hand, you can do randomly. Partner is third one. So third is different from the second, right? That you have to take care. Phi is also 0.18. So this phi value you can keep constant for all the solutions, or that phi value you can change for every solution. There is no restriction on that. Then you create a new solution by using that formula, bound the solution, perform the greedy solution, update the solution and track. Assume after considering this one, what is happening, right? We are not getting a better solution. So with this consideration, whatever the second solution is there, 3197, the modified solution is 2 dash is not a better solution. So what we have to do? You see, this trial counter is incremented by 1. Previously it was 0. Now the trial counter is 1. And this is the previous solution is there, 3197. Okay. So with this, your employee B phase for the second solution is over. Now consider for the third one 0315 with this consideration. First variable you want to change, partner is 1, so 1 is not equals to 3, right? 5 equals to minus, so here 5 value I am changing in every solution for the employee b phase. You can keep constant also. Create new solution, bound solution, greedy search you do, update solution and turn. Let us assume with this consideration we are unable to get a better solution from 0315 also. Now you see that in the previous case, your trial counter for the third solution is 0. Same solution we are keeping 0315 because we are not getting a better solution. So the trial counter is incremented by 1. With this, employee B phase for the third solution is over. Now go to the fourth one, 2149. Same some consideration, not the same consideration. You have to randomly consider these things. Second variable you want to change, partner is third, so third 3 not equals to 4, right? So the solution and the partner must be different. 5 equals to minus 0.6, same. Create the solution, new solution, bound it, perform the greedy selection, update the solution and the type. Assume 2145, also we are not getting a better solution. Again the trial counter is incremented by 1. So the same 2149, whatever value was there, same value we are keeping in the population. Now only one solution is remaining to be performed by the employee B. Right? That is a 1283. So for 1283, now this same steps you have to follow, but with different parameters, right? So the fourth variable we want to change. Partner is 3. So 3 not equals to 5. It is satisfied. Let us assume 5 equals to 0.81. Now create the new solution for that fourth variable, bound it, apply the greedy selection, update the solution and the try. And let us assume with this consideration 1283, we are able to get a better solution. Now you see this value is changing. This fourth we have considered now, fourth variable. This is changing and this is a better solution, right? So the trial counter will be reset to 0, right? So with this, your employee B phase is over for this particular problem, right? So we are having 5 food sources or the 5 solutions. So when we have tried to perform the employee B phase, we are able to get 2 better solutions, that is for the first solution and another for the second solution, sorry, last solution. That's why for the first and the last solution, my trial counter is reset to 0, but for the second, third and fourth, my trial counters are incremented by 1. So we have started with the initial population. If you remember, I think this is the initial population. This is not the initial population. 4018 something. This is the initial population, right? Now after applying the what do you call, that is the employee B phase, here we are getting a change and here we are getting a change, right? So a new population we are getting after doing the employee B phase. Yes. So this is the output of your employee B phase. Okay. So we have started with 5 populations. Now after the employee B phase also, we are getting a, what we are getting? We are getting a population, right? Having size 5 and the 5 solutions are there, right? So what is happening, if you see in this case, the initially generated solutions, right? What was your minimum value? If you remember, just let me check, I forgot. If you see, this is the 35, right? Some of the solutions objective value is changing here, right? 35, this 81 is changed and this 78 also changed, right? 81 changed, 78 changed. This one, not this one, this one. This is changed from 81 to 80. This is something was there, it is changed to 70.9. Right? Now let us go to the next phase, that is the onlooker B phase. So as I told, before doing the onlooker B phase, what you have to do, you have to determine the probability value of each food source, right? So the probability, some formula I told you, right? 0.9 into 1 plus that fitness by maximum fitness plus 1, right? So if you use that formula, you will get 0.5 for this first solution, 0.33, 1, 0.41, 0.55 for the subsequent solutions. So for what purpose we are using this probability value? So this probability value is used to decide whether the onlooker B will get a chance to change a food source. I mean to exploit a food source or to change a solution. Huh? Now let us do for onlooker B. Now OB1 it is trying to explore this one. So what is happening, right? Let us see that one. So for that, in order to perform the onlooker B phase for the first solution, now our first solution is 4008, right? So we have to select a random number. If you remember that concept, random number 0.39 assume. If that random number is less than the probability of that food source, then it will exploit the first food source. Exploit means it will try to change. Again, changing, you see, same thing, whatever we have done in the employee phase. Same formula, right? So you have to select a random variable again to change, right? Let us assume the variable is 4. This value we want to change. Partner is 3. So 3 not equals to 1 because first solution has to undergo the onlooker P phase. So this is the 5. Let us assume phi equals to minus 0.68. So if you apply that function, right, you will get 5.96. So now 4008, now we are getting 4005.96. As this is a very small dimension problem, right? And this is a minimization problem. You can understand that this is a better solution, right? So after doing the onlooker B phase, the solution 1, whatever modification we are doing, we are getting a better solution. So the updated solution will go to the population and the trial counter will be reset to 0. That is the minimum. If you see, previously it was 4008 after the employee B phase. Now this is 5.96. So corresponding objective value and the fitness value is there. So the trial counter is reset to 0. So with this, the onlooker B phase for the first solution is over. Right. Next, what you have to do? You have to apply the onlooker B phase to the second solution. That means OB2. Now OB2, onlooker B2 will try to exploit this food source 3197. Right. So for that again you have to choose a random number. So 0.2, this is less than 0.33 because probability of second solution is 0.033. So probability already we have determined here. Okay, so this is 0.2 is less than 0.33. So it will try to exploit. So exploit means it will try to change the jth bit of that second solution, right? So which one is the jth bit? So for that you have to determine which variable you want to change, what is the partner, what is the phi value, then apply that equation to find out the new solution, bound the solution if required, then evaluate the fitness function in order to do the greedy selection, then update the solution and update the track. So whatever we have done in the employee B phase, only that random number we are generating, and by comparing that random number with the probability value, we are deciding whether that solution has to undergo change or we have to go to the next solution. That is the meaning. So let us assume that with this consideration, the solution 2, right, we are getting a better solution. So by doing this one, we are assuming that the change, second one, whatever we are changing, we are getting a better solution. So this is the changed value, third bit. And if you are getting a better solution, previously if you remember, the trial counter of second solution was 1, right? Because whenever we have done the employee V phase for the second solution, we didn't get a better solution. So the trial counter was incremented by 1 during the employee V phase. But during the onlooker V phase, we are getting a better solution. So this will be reset to 0. Okay. With this, the onlooker B phase for the second solution is over. Now go to the third one. Same thing you have to do. So 0315, third one. And assume the random number is 0.57. So 0.57 is less than 1 because the probability of third solution is 1. Already we have determined. So it will exploit the third food source. That means it will change the third solution. So which bit? Let us assume the second bit of the second variable we want to change. Partner is 4. Phi is 0.07. Now create the new solution. Bound it if required. Evaluate the fitness function for doing the greedy selection. Then you update the solution and update the trial. So with this consideration, what is happening for the third one, right? I think we are not getting a better solution, right? So now you see the trial 3, whatever previous value 0315 is there, but this trial counter is incremented by 1. So that is the trial counter is 2. Okay. Now let us do for the fourth one. So with this the onlooker B phase for the third solution is over, up to third over. Next we have to do for 2149. So with this 2149, let us consider a random number which is greater than the probability value. Then you can see how the it is resetting to 1 again, right? So we are doing the onlooker B phase for the fourth solution now, 2149. That means OB4 is trying to exploit the solution S4, right? So put source is X4, okay? Random number we are generating 0.95. So here the probability of fourth is 0.41. So 0.95 is greater than 0.41, right? That means it cannot exploit the food source S4. So which one it will exploit? It will try to exploit the solution S5. That is the meaning, right? So here R is less than P4. So the B will not get a chance. This is the onlooker B. Yeah? B means onlooker. We are doing the onlooker B phase. So the onlooker B will not get a chance to exploit the fourth food source. So it will check for the next food source, that is the fifth food source. Again, same procedure you have to follow. Now we are doing the onlooker B phase, right? For the fourth solution. But for the onlooker B is unable to exploit this one, so it will try to exploit this one, right? S5. So the next food source selected X5. Let us generate a random number 0.54. This is point less than 0.58. So it will exploit. If this is greater than, suppose we are generating a random number 0.8. 0.8 is greater than 0.54. So what will happen here? This OB4, it will not also get a chance to explore the S5. So again, it will go back to S1. It will try to explore S1. That is the meaning. Okay. So here, as the random number we are generating, this is less than the probability of that fifth one. So it will try to exploit the fifth food source by using the same equation, right? You decide which variable you want to change. That is the J first variable. Random partner is 2. So 2 not equals to 5, right? Because the fifth solution we want to change. 5 equals to 0.7. These are all your random values only, right? You can do these things, this thing, this thing, this thing. But in that range, you have to select. This value it should be -1 to 1. Partner, this should not be equals to the solution, which solution you want to change. And this value should be between 1 to dimensions, number of dimensions present in the problem, right? Then you create the new solution, generate the bound if required, right? Then evaluate the fitness function for the greedy selection, update the solution and the try. So if you do this one, what will happen with this consideration? The fifth one, right? Fifth one, we are getting a better solution now. See. So fifth one, we are getting a better solution at this point. So the trial counter is reset to 0. So with this, the onlooker B for the OB4 we have completed, right? We have seen OB1 exploited S1, OB2 exploited X2, OB3 exploited S3, OB4 didn't get a chance to explore S4, so it tried to explore S5. This we have done till now, right? Next OB5 is there, right? So OB5 what it will do? So S5 up to S5 it is over. So OB5 will get a chance to explore the solution S1 again. So how many times the solution S1 is getting a chance for undergoing changes here? 2 times, right? Because the probability is higher here, right? So perform the onlooker B phase for the fifth solution. So as all the 5 food sources have been exhausted from OB1 to OB4, so only 4 B's have underwent the onlooker B phase. So we have to select the first food source. This one, whatever I told. OB5 will get a chance to explore the S1. Right? So same thing you have to do again. So now this is OB5, right? We are trying to OB5 we are trying to exploit S1. We are generating R. If R is less than P1, then it will exploit. Otherwise, if this condition fails, I mean if R greater than P1, it will get a chance to exploit S2. But for this consideration, our random number it is satisfying less than P value. 0.41 is less than 0.5. So the new value you calculate, this is the new value equals to the old value plus 5 into a difference between the jth bit of the current solution and the partner. Okay. Then select which variable you want to change. This is the first variable. partner is second, so 2 not equals to 1, right? First, for the first solution we want to change, partner is S2, right? So both are different. Phi equals to minus 0.87 in the range minus 1 to 1. So create the new solution, bound it, evaluate fitness function, do the grid selection, update the solution and the try. So with this consideration for the first solution, what is happening, we are getting a better solution here. Previously, if you remembered, it was 4, right? So this is a minimization problem. 3.13 means this is the better solution. Only one bit you are changing. So the trial counter is updated to 0, reset to 0, right? So with this, your onlooker B phase is over. So we have started with 5 random solutions in the population. We have applied the employee B phase. Again, you got a new population, then we applied the onlooker B phase and we got this population. Right. Next, we have to decide whether we have to go for the scout B phase or we have to terminate here. Right. In the scout B phase, right? So scout B phase, it may or may not happen. It depends upon the limit value. So for showing only what will happen in the scout B phase, I have initialized the limit value equals to 1, right? So limit value is 1 means the higher value you have to first choose. So this solution, if you see the trial value is 2, which is greater than 1. So this solution or this food source will be exhausted. So exhausted means this is the abandoned solution, you have to replace. If you see this population, this solution is also the best solution, right? So during the depending upon the relation between trial and limit, it may happen that some of the good solutions also you are discarding. So in order to lose that information before doing the scout B phase, I mean after the onlooker B phase, we are memorizing the best food source. If you remember the algorithm, if we'll come back to that algorithm, we are performing the employee B phase, we are performing the onlooker B phase, we are memorizing the best solution here, I mean the best food source, then we are applying the scout B phase. Because scout B phase, it is randomly exploring the food sources, right? So the that is the best solution we are memorizing after the onlooker B phase, so that we will not lose any good information after the onlooker B phase. So for this particular example, this limit trial value is 2. So this is greater than your limit value. So this solution we have to discard. Right? Even if we are discarding, we are memorizing the best solution. So the best solution so far equals to 0.315. Right? For this one. Right? So this one we are memorizing. So even if we are replacing it with another solution, we are not losing this information. Right? Now let us go to the scout B page and we'll see what is happening here. Now you are memorizing the best solution, store the best population member and its objective function value. So for this particular example, you are having 0.315 with the objective value 35. Okay. This one, B value are storing. Then we are selecting the solution which trial is greater than the limit. So for the problem, same. For this given problem, same solution we are getting which trial is greater than limit. So we have to reject this solution. Right? We have to discard this solution with a new solution. Right? So we have to replace this x3 with a new random solution. So we are having now 5, x1, x2, x3, x4, x5. For this, my trial counter is greater than limit, whichever is higher value consider. That we are replacing. So this, whenever we are replacing this value with a random solution. As we have seen the scout V phase, we are exploiting the food sources randomly. Okay? There is no logic behind that. Only random solution we are generating within the lower bound LB and the UB. Okay, so now you generate the new solution by using this LB plus difference minus UB minus LB into a random number. So this follows the right uniform distribution in the range 0 to 1. Right. So by using this one, you can generate a new solution, and this x3 will be replaced by xb. And this trial counter, if you see here, this is the output, right? So this is the output we are getting after the scout, after the onlooker B phase. So this we are removing, discarding in the scout B phase. So this trial counter for the new solution we have to reset to 0, right? So if you apply this one, you will get x new. Maybe we are getting this one x new. We are getting generating four new values. With respect to these four values, what is the f of x value? What is the fitness value? And the trial calculator, if you see, this is the zero. Remaining are same. 0, 0. This is 0, 1, 0. So 0, 0, 0. This is the resetting 1 and 0. Right? Until now, our best solution, because we are memorizing the good solution, right? Best solution is, I think, what is that value? 031535. Okay, let us memorize the fitness value only, 35. Best solution is 35. Right? So we are not losing this information. Even if we are discarding that best solution, we are storing somewhere, because this value we have to update in every iteration. So with this, your first iteration of ABC algorithm completed. Right? Now you have to go for the second iteration. So the second iteration, what you have to do? Now your population is this one, with the trial value this one. So you have to repeat whatever we have done, right? We have to apply again the employee B phase. You have to apply the onlooker B phase. You have to apply the scout B phase if required. That means if the trial value of any solution after the onlooker B phase is greater than the limit value, right? If you are doing, then you replace, memorize the best solution, memorize the best solution, then you do the replacement, right? So this best solution, the next iteration, if you are getting any solution which is value is 30, right? So the best solution will be updated from 35 to 30. So like this, if you iterate for capital T number of iterations, right, at the end of the iterations, you may reach towards the global optimum solution for a given problem. So this is all about the theoretical concepts of the ABC algorithm. If you are having any doubt with respect to this theory, you can ask me. After that, I will go for the MATLAB demo. Any doubt? So give me 2-3 minutes break. After that, I will start the MATLAB code. Let me open the MATLAB editor. Okay, this ABC algorithm ABC. So I will show you the MATLAB code for. mm, uh, if you are having the idea about the artificial neural network, right? You know, generally we are using the standard backpropagation algorithm to train a neural network, right? Suppose we are having this neural network. We are having two inputs in the input layer. Assume we are having two hidden layers, sorry, one hidden layer having two hidden neurons and one output layer, right? So this is a fully connected network. So these are the weights, okay, and these are the biases. These are the weights, okay. These are the biases associated with everything. Right? So this training of the ANN you can do by using this ABC algorithm. This is the x1, this is the x2, this is the y, right? So in the backpropagation algorithm, what you are doing, you are forward passing the input from the input layer to the output layer, and during backpropagation, what you are doing, you are backpropagating the error from the output layer towards the input layer. Forward pass, then you are doing the backward pass, right? So there are some, right, your derivative you have to take, and you are trying to minimize the error whenever you are training the ANN. So this, whenever you are applying the backpropagation algorithm, you are trying to update the values of all the weights. This one, right? These weights you are trying to update. I mean, you want to optimize. These are the biases. These are also biases, right? So every neuron, they are having some activation functions, right? Suppose this is X1, this is W11, W12, this is W21, that's W22. This is, assume your W31, something like that, right? So what it is doing, suppose this is using your sigmoid activation function in the hidden layer, right? So what input you will get, it will get the input x1 w11 plus x2 w21. This information it is getting, right? Then what this neuron it is doing, it is, as it is using the sigmoid activation function, it will calculate 1 by 1 plus e raised to the power minus 6. So this will be the output for this layer, right? Again that output, this is suppose h1, this output will be h2. Again you have to take the dot product of two these two you have to add, and then suppose this is the linear activation function, then you have to consider h1 w31 plus h2 w32. So this will be your y. So y equals to this. Right? So this is a procedure for doing the forward pass, and during the backward pass you have to pass the derivative of the error with respect to the weights and the biases. So ultimately this can be formulated as an optimization problem where you want to optimize the value of W11, W12, W21, W22, W31, W32. Suppose this is B1, B2, B3, and the biases B1, B2, B3. So these are the design variables of the given problem. And what will be the objective value here? Objective value may be the difference between the actual value and the predicted value. So you can consider the MSE, mean square error, between your actual and predicted. So for the actual value of y is 2, but you are predicting this as 1. So what is the MSE, mean square error? So 2 minus 1, that means 1. So this is 2 minus 1 square. So the error is 1. So this MSC we want to minimize by using the ABC algorithm. Right? So for that only I want to show you the demo in the MATLAB. Mm. Okay, so this is the neural network training, right? This is for the neural network you are training for a XOR problem, right? Which is having two inputs and one output. So XOR problem, whenever both inputs are 0 or both inputs are 1, the output will be 0. If any one of the input is 1, the output is 1. That is the training we have to do, right? So this thing I am not going to discuss because this is the related to whatever the dot product I told you, and whatever the depending upon the sigmoid, depending upon the activation function used in each layer of the hidden layer and the output layer, the y, the network's output will be predicted like this, right? So your objective value is MSE between the what is the predicted value and what is the actual value. So we are trying to minimize this MSE value by using the ABC algorithm. So here instead of this NNN train, this function, you can use the sphere function also, right? Whatever you have used. For the sphere function, you have to change the number of dimension that you have to change here in the ABC algorithm, right? So now let us see the ABC algorithm. So what are the parameters here? Your NP equals to the 50, population size 50, right? This is the swarm size, not NP is the swarm size. Food number, your employee B equals to 25 and your onlooker B equals to 25. Then this is the number of iterations, this equals to 100. Okay. Then this is the objective function, which This is the problem which you want to solve. Like yesterday I have shown you the D, na? Like that you can use the sphere function here also, and some modification here you have to do, because this program is written for your training the neural network. Okay, so we have seen for this particular problem D equals to 9. And 6 weights are there, 3 biases are there. That's why D equals to 9. So if you want to solve the sphere problem, then dimension you have to change here. Okay. So assume the lower bound and the upper bounds we are fixing as minus 10 to 10. Lower bound is 10, upper bound is plus 10. So limit, as I told you, this is the food number into T, right? The number of bees into the dimension of the problem that I have initialized. So only one time I am running the algorithm, but how many iterations? 100 iterations I am solving, right? Okay. So for the first time we are running, so what we are doing? 1 minute. Okay. So we are generating, right? You have to generate the initial population, right? So this part is for generating the initial population, right? And this is for calculating the objective value and the fitness value of the solutions whatever you have generated. Then you have to reset the trial counter for every solution as 0. Initially you have reset the trial counter as 0. Then we have to memorize the best food source so far, right? So whatever we are initially generating, what is the best food source, you keep there also. Then after onlooker b phase also, you can update that best food source. Okay. Next, for each iteration, right? For iteration equals to 1, so while your ITR less than equal to maximum cycle 100, so first phase you have to do the employee b phase. So in the employee b phase, what you are doing, employee b phase, right? For every food source you are doing that one, right? So which parameter you want to change, this is the which variable you want to change, this is the word. Then random partner you are choosing, right? Then random partner should be different from the solution whatever you are considering, because the current solution and the random partner should be different. Then you are applying that equation, your modified solution equals to your previous one plus 5 into xj minus x min. That part you are applying. Then what you are doing, you are doing the bounding. Here you are doing the bounding, corner bounding you are doing. After doing the corner bounding, you are doing the greedy selection. So doing the greedy selection, you have to again evaluate the, or you have to find out the fitness value of individual solution here, right? Then you, during the greedy selection, what you are doing, you are comparing two solutions, right? Whatever previous solution or the updated solution. If you are getting a better solution, then your trial you are resetting to 0. Otherwise, the trial counter you are incrementing by 1. So this you are doing for each and every solution in the food sources, right? Then you have to go to the second phase, that is the onlooker B phase. So before doing the onlooker B phase, you have to calculate the probability of each food source, right? This formula already I told you. Then what you have to do in the onlooker B phase, so for every food number, right, you are generating a random number. That means for every onlooker B, you are generating a random number. If that random number is less than the probability of that food source, right? So what you are doing, you are trying to exploit the food source. So during exploitation, whatever code we have written for the employee B phase, this part is same. Up to which one? Up to your updating the trial data. This is same. Okay. After that, what we are doing? We are incrementing the value I equals to 1. Then we are reaching to the last one, right? If I equals to food number plus 1, that means if I equals to n, if you remember, we are resetting the n value equals to 1. So this is the that part, right? So with this, your onlooker B phase is over. Next, we have to, again, after the onlooker B phase, you update the best food source if you are getting a better solution in the objective in the onlooker B phase, after the onlooker B phase compared to the initial best food source, right? So this only you have to compare between the first best food source whatever you have done and whatever you are getting from the onlooker B phase, that you are updating here. So you are updating the best food source, I mean the best solution, before entering into the scout B phase, right? So how to determine whether you have to perform the scout B phase or not? For doing the scout B phase, you are comparing the trial of individual solution with the limit. If the trial of the particular solution is greater than limit, so what you are doing? You are discarding that solution and you are generating a new solution by using this one. LV plus UV minus LV into random number. Right? And that solution you are adding to the population. And the trial of that population you are keeping as 0. Right? So with this, right, your one iteration of the given program is over. Right? So next what you have to do, whatever minimum value you are getting in the population, all the values you are storing here, that you have to return as the optimum solution of the given problem. Right? So if you run here, this is the mean square error it is showing for the neural network training. Okay, this number of iteration is 100. So it will take some time, 1 minute, maybe 1 minute it will take. Let us see, if you see the mean square error, with every iteration you see, it is changing, right? That means we are able to minimize the objective value. So objective value is the mean square error whenever we are training the neural network. So what is the mean square error between the actual value and the predicted value? Okay, it will take half minute. Right. Now say the 100 iteration, right? You are getting 5.79 into 10 to the power minus 5. That means something 0.00005, right? As you like that, you are getting this one. So if you see the first iteration, the value was 0.18284. So if you see the subsequent iterations, we are able to minimize the mean square error for training the artificial neural network to solve the exert problem. Right? You can consider, you can check the sphere function. So depending upon the sphere function, some of the parameters you have to change in the ABC algorithm. Then only it will work for the sphere function. Right? You can call the sphere function and you can change the required parameters in this program. So it will optimize the, it will minimize the sphere function also. Right? So whatever modification you want to do for a particular problem, you can use this problem to solve any optimization problem by using the ABC algorithm. Okay, so this is all about this ABC algorithm. If you are having any doubt, any questions, you can